My dear students, a very good afternoon. I'm back with the leftover lecture which I had delivered last time. It's 5:40 in the evening. Let's complete what was left in the last lecture. In fact, in our last lecture, we were discussing about principal components of an HVDC power transmission system. We have identified various parts of power transmission system, and out of which two very important components or parts we have already discussed. One was the converter itself, and we have seen that in traditional or conventional HVDC systems, we use current source converters using thyristors or SCRs, and in modern HVDC systems, which we also call HVDC Lite or HVDC Plus, we use voltage source converters using IGBTs or GTOs. The other part that we discussed last time was converter transformers. We have seen that it is a special transformer because it has to handle harmonics, it has to handle transients, it should be fitted with online tap changing and so on. The third important part that we are going to discuss today is smoothing reactor. Smoothing reactor. You have seen in last lecture, we had an HVDC system like this, a bipolar HVDC system, and we have a smoothing reactor, LD. The current flowing is ID. What is the function of this smoothing reactor? The main function of this smoothing reactor is to smoothen, that means to remove the ripples in the transmission line current, that is DC current ID. The ID may contain ripples, it may not be very smooth in nature. So to smoothen this current, to remove the ripples in this current, we use this smoothing reactor, LD. This is the main function. So I will write here, main function is to remove ripples in ID. That is to smoothen ID. It smoothens ID. Smoothen the DC line current or transmission line current ID. This is the main function. Another function is that it decreases the rate of rise of current. Suppose a fault occurs on the inverter side. This is the inverter side. If this is the rectifier side, this may be the inverter side. If a fault occurs on the inverter side, in future you will study in one of the classes that a fault on the inverter side results in commutation failure. Now I hope many of you or maybe all of you know what's a commutation failure. So an inverter fault will instantly result in commutation failure. But what happens if a fault occurs on the inverter side? What this LD does, what the smoothing reactor does, it reduces or it decreases the rate of rise of current. That is did by dt. It limits the rate of rise of current is reduced. And therefore, it helps in the prevention of commutation failure. How does it help in the prevention of commutation failure? By decreasing the rate of rise of this fault current. We will study in one of the classes. So these are the two main functions of smoothing reactor. Now, the smoothing reactor, as far as its construction is concerned, it comprises of total or partial magnetically shielded partial air core with magnetically shielded. It's a total or partially air cooled magnetically shielded reactor. So it is either totally air cooled magnetically shielded reactor or partial air cooled magnetically shielded reactor. And as far as its winding is concerned, it has got the disc type winding. Disc type coils are wound around it, and these coils are braced to the core so that in the event of huge currents like faults, short circuit currents, they are very strongly, they are very strongly on the core. They are not thrown out of the core. So that's why they are braced on the core. So that is about the third component, that is smoothing reactor. And do you know what is the value of this smoothing reactor? It is not in microhenry or millihenry. It is in henries. It may be 1 Henry, it may be 2 Henries, or it may be 3 Henries, or maybe more than that. Imagine a 2 Henry or 350 hertz reactor. It's a huge reactor. So that is the third part of your HVDC system, that is smoothing reactor. Fourth part is harmonic filters. Harmonic filters. Now, why do we need harmonic filters? You know, in an HVDC transmission system, we have converters on both the sides. In one converting station, we have converters. In another converting station also, we have converters. And you have already studied these converters, their operation in your basic power electronics course. When these converters draw the current, they don't draw, especially at a certain firing angle or delay angle, they never draw sinusoidal currents. They draw distorted currents, which are very rich in harmonics. And when these currents flow in the transmission, in the AC system, they cause harmonic voltage drops, and these harmonic voltage drops result in the distortion in the voltage, AC voltage, which is available to AC loads. So therefore, our aim should be that these harmonic currents should not be, present on the AC system. Although they are drawn by the converter, they are drawn by the rectifier, controlled rectifier, but they should not be allowed to pass on the AC system, because they will otherwise cause harmonic voltage drops, and thus they will distort the AC bus voltages. All right. So how do we arrest these harmonic currents? How do we stop them? How do we stop these harmonic currents from passing into the AC system? By using the filters, and these filters are called harmonic filters. Now, as far as harmonic order in the line current is concerned, this harmonic order is given by this equation: H is equal to NP plus minus 1, where P is pulse number, and N is an integer. Like N can be 1, 2, 3, 4, and so on. It's simply an integer. Now we have two types of converters. Generally, you deal with two types of line commutated or phase controlled converters in HVDC transmission systems. One is 6-pulse converter, and another is 12-pulse converter. If you have a 6-pulse converter, I will write here for 6-pulse operation. I mean, if you use 6-pulse converter, that will give you 6-pulse operation. What is the pulse number? P is equal to 6. Therefore, what is the harmonic order? It is NP plus minus 1. Let us take N1. So 6 into 1 means 6, plus 1 is 7, and 6 minus 1 is 5. So 5 and 7. The most predominant harmonic will be 5th. It will be followed by 7th. For N equal to 2, so 2 6 are 12, 12 plus 1 is 13, and 12 minus 1 is 11. So next predominant harmonic is 11, next is 13. For N equal to 3, it is 6 3 are 18. 18 minus 1 is 17, and 18 plus 1 is 19. So 17, 19. So for N equal to 4, it is 23, 25, and so on. These are the harmonics in the current, line current, which is drawn by the converter from the AC side. Okay. So the most predominant harmonic is the 5th harmonic, followed by 7th harmonic, followed by 11th harmonic, followed by 13th harmonic, and then higher order harmonics. Although higher order harmonics may not be of concern for us, because higher the order of harmonic, smaller and smaller becomes their magnitude, and they are not a matter of concern. But what is the matter of concern for us is these lower order harmonics, 5th, 7th, especially 5th, 7th, and 11th, and sometimes we take 13th harmonic also into consideration. We suppress it. 30th onwards, that is 17th, 19th, and etc. They are higher order harmonics. They are otherwise also negligibly small. We don't bother about them. This is for 6-pulse operation. For 12-pulse operation means if you are using 12-pulse converter, that will give you 12-pulse operation. So for 12-pulse operation, pulse number is 12. So therefore, what is the harmonic order in the line currents? For 12 minus 1 is 11, 12 plus 1 is 13. So the most predominant harmonic will be 11th, followed by 13th. For N equal to 2, 2, 12 are 24, so it will be 23 and 25. For N equal to 3, 312 or 36, so it will be 35, 37, and so on. So the most predominant harmonic in a 6-pulse converter is 5th harmonic, whereas in a 12-pulse converter, the most predominant harmonic is 11th harmonic. In fact, this is one of the advantages offered by 12-pulse operation over 6-pulse operation. That is, these lower order harmonics, 5th and 7th, are automatically absent in 12-pulse operation. So the most predominant harmonic starts from 11th harmonic. 11th harmonic followed by 13th harmonic. Now, how many harmonics do you need to suppress here? Mostly 11th and 13th. 23rd is not of a concern, 23rd and higher order harmonics. So therefore, to remove these harmonics, what type of harmonic filters do you require? For 6-pulse operation, let us assume that we have to remove 1, 2, 3, and 4 harmonics. 5th harmonic, 7th harmonic, 11th and 13th harmonic. And if you have a 12-pulse operation using 12-pulse converter, then we may be supposed to suppress 11th and 13th harmonic. So therefore, for suppressing these harmonics, you need filters, and those filters are called harmonic filters. Now, these harmonic filters are tuned to a particular frequency. For example, if you wish to suppress 5th harmonic, you have to design a single tuned filter which is tuned to this 5th harmonic frequency. So it suppresses only this 5th harmonic frequency. It cannot suppress other order harmonics. For suppressing or for eliminating 7th order harmonic, you need another single tuned filter which is designed to arrest or to suppress or to eliminate the 7th order harmonic. Similarly, for suppressing 11th order harmonic or 13th order harmonic, or in this case 11th and 13th order harmonics, you need single tuned filters. So here you need 4 single tuned filters, here you need 2 single tuned filters. So you need single tuned filters. And these single tuned filters are tuned to a particular harmonic frequency, the harmonic order which you want to eliminate, which you want to suppress. And they very successfully suppress that harmonic. And these filters are called harmonic filters. They are called harmonic filters. So this is the main purpose of these harmonic filters. Now, these harmonic filters are very large in size. For suppressing 5th harmonic, you need a 5th harmonic filter, which is an LC filter, which is designed for a frequency of 5 into 50, that's 250 hertz. 250 hertz is not a higher frequency, it's a smaller frequency. So at smaller frequency, the size of magnetics, L and C, is very, very large. Therefore, if you visit the switching yard of an HVDC converter station, in the yard itself, you will see large inductor and capacitor banks. And those inductor and capacitor banks are nothing, they form these harmonic filters. So what is the other function? This is the primary function of harmonic filters. What is the secondary function of harmonic filters? At fundamental frequency, they provide some sort of reactive power compensation. What is your fundamental frequency? Well, fundamental frequency is 50 hertz. For example, if you have a 5th harmonic, a single tuned filter tuned to 5th harmonic, it will suppress 5th harmonic component. Similarly, another single tuned filter which is tuned to suppress 7th harmonic component in the line current, it will suppress 7th order harmonic in the line current. But at the fundamental frequency, these harmonic filters will provide some reactive power, not all reactive power, some reactive power. So therefore, we can say that these harmonic filters provide some reactive power compensation at fundamental frequency. So that is about harmonic filters. Next is, 5th part is overhead lines. Overhead, that is OH lines. If you are using an overhead HVDC transmission system, just like AC transmission system, you need transmission lines. These are called overhead lines. The configuration and the construction and the design of these overhead lines is almost same as that in case of AC power transmission system. Okay. Now these overhead lines are supported on the cross arms which are having insulators. The size of the insulators and you can say the size of these cross arms, the clearance of cross arms, it will be decided by the voltage. For example, if you have a plus minus 400 kV transmission line, so accordingly you will decide about this clearance of cross arms and the insulators. Now, as you already know, we have three types of HVDC links. We may have monopolar link, bipolar link, or homopolar link. In case of monopolar link, you need only one pole. Only one pole is needed there. Ground or C acts as a return path. So it's the simplest possible construction. So if your HVDC system is a monopolar HVDC system or it's a monopolar link, the line construction is simplest. But as you already know, we don't use this monopolar system. We don't use even homopolar system. The most popular link is bipolar link. In case of bipolar link, you have two poles. One is positive pole, another is negative pole, and therefore the transmission lines have to be laid and they have to be supported over the transmission towers. The construction, the configuration, the design of these conductors, the transmission lines is similar to that of AC transmission systems. Now, generally bundled conductors are used, as in case of AC transmission systems, we use bundled conductors. Bundled conductors are used for reduced corona loss. Reduced corona loss. Okay. So this is about overhead lines or overhead conductors, transmission lines. Next part is reactive power source. Sixth, reactive power source. You know, our transmission system is DC transmission system, and there is no concept of reactive power in a DC circuit. And why does your HVDC transmission system draw a large amount of reactive power from AC source? What is the source of this reactive power? Converters, line commutated converters. You must have studied in your BTech Power Electronics course that when you operate a line commutated or a phase controlled converter at a particular firing angle or a delay angle, there is phase displacement between fundamental component of current and the source voltage, and that deteriorates the power factor, that makes power factor less than unity, and power factor less than unity means that your system is drawing reactive power. So therefore, these line commutated converters in both the converting stations, a rectifier converting station as well as inverter converting stations, at both the stations you operate these line commutated converters at a particular delay angle or firing angle, and they draw the fundamental components of currents which lag behind the voltage, and therefore they draw the reactive power. They are the sources of reactive power. As such, otherwise on the DC line there is no reactive power flow, because there is nothing like reactive power in a DC circuit, but it is your converter which draws the reactive power because of its operation at a particular delay angle or a particular firing angle. It has been seen that the reactive power requirement of your converter is 50 to 60% of real power flow. This reactive power requirement is nearly 50 to 60% of real power flow. Real power which you actually are transmitting over the line. So it's a huge requirement. So therefore, this requirement will burden your whole AC system, because ultimately this reactive power will come from your AC system. So therefore, you need a reactive power compensation. So what type of reactive? At the converter terminals itself, you connect your reactive power compensator across your converter. So that whatever reactive power is required by your converter, that does not come from the generators, that comes from the reactive power source itself, a compensator itself on both converting stations. So normally two types of these reactive power compensators are very popularly used in HVDC converting stations at the converter terminals. They are synchronous capacitors, or what you commonly call as synchronous condensers, or shunt capacitors, shunt capacitor banks. Whether to use a synchronous condenser or a shunt capacitor bank, it depends upon the location of the converting station. If the converting station is closer to the generator, then we generally prefer, technically it is preferable to use synchronous condenser for reactive power compensation at the converter terminal. And if your converting station is close to the load center, for example, your inverting station, which is far away from your rectifier station and it is closer to the load center, there we don't use synchronous condenser generally. There a bank of shunt capacitors is used for reactive power compensation. So that means you need huge these synchronous condensers and reactive power compensators at your HVDC converting station, which adds to the cost of the terminal equipment. These compensators will be part of your terminal equipment, so it adds to the cost and size of the equipment. That is about reactive power compensation. Next is earth electrodes. Seventh very important part is earth electrodes. You have seen in your HVDC transmission systems using bipolar link. I will show you the one converting station only. We ground, the neutral or the junction point of the converters is grounded on both sides. I'm showing one side, same is the case with the other side. So how is this grounding performed? How is this grounding? How does this grounding take place? How is this grounding actually done? We use earth electrodes, large earth electrodes. Do we put earth electrodes on the surface of the earth? No, because the resistivity at the surface of earth is very, very large. I will write here resistivity of earth's surface is very large. It's quite high. It is nearly 4,000 ohm meter. The resistivity of the surface of the earth's surface is very high, nearly 4,000 ohm meter. So therefore, and it is very difficult to put your grounding rods or earthing rods at the surface and to support them at the surface. Okay, and earth surface has very high resistivity, 4,000 ohm meter, and it will result in large transient voltages in the event of faults. It will also result in large, potential gradient around the electrode, and it will put public safety in danger. So therefore, we never put the electrode at the surface of the earth. What we do is that we bury the earth electrode inside the earth, deep inside the earth. The resistivity inside the earth is very small. The resistivity inside the earth is generally just 3 to 10 ohm meter, very, very small. As you go deep inside the earth, the resistivity drops appreciably and it decreases to this numerical value, just 3 to 10 ohm meter, which is preferable. And in fact, this earth resistivity is, it changes, it varies from place to place, and it also depends upon the geographical location. For example, if there is nearby there is a water body, then earth resistivity will be low, and at very other places, hot places, dry places, earth resistivity may be comparatively higher. So therefore, this is the earth resistivity. Now the location of this earth electrode is also very, very important. Can we put the earth electrode at any place and then lay put it at any place? Answer is no, because the location of earth electrode is very, very important. How it is important? If you put an earth electrode near a power line, there is already a power transmission line going on, and just below that power transmission line you are putting earth electrode. It will cause, because the current which is flowing through the earth current, which is basically ID, the transmission line current, DC line current, it has got some ripples, and these ripples cause interference they may cause interference with the power lines. And if a telephone line or communication line is also passing nearby, the current flowing through the earth will cause, communication or telephone line interference also. And if there is a railway signal nearby, it will cause interference with the railway signals also, which may be very, very dangerous for the safety of the passengers traveling in the trains. Because if the railway signals are disturbed, that may result in an accident, in a mishap. So therefore, another thing is public safety. You cannot put it just at any place of your choice. The choice of the location of earth electrode is very, very important. You have to consider all these factors. Wherever you bury the earth electrode inside the ground, you have to see whether there is a power line. If power line is there, or telephone line is there, or railway signal is nearby, don't put it there. Just go away and put it at some other place. Okay. And as far as this earth electrode is concerned, its resistance of earth electrode is very, very small, 0.1 ohm only. And how deep earth electrode is buried? Earth electrode or grounding electrodes are buried deep inside the ground, nearly about 500 meters inside the ground. This is it. This is about earth electrode. So that is all about various components, principal parts of an HVDC power transmission system. We have started. First, we have drawn the schematic diagram of a bipolar HVDC link, and from that HVDC transmission system, we have identified various components. What were the various components? Phase controlled converters or line commutative converters, converting transformers, smoothing reactors, okay, reactive power compensators, overhead lines, earthing electrodes, and harmonic filters. About 7 main components we have identified, and this is in addition to the protection system. We are not discussing about the protection system. Protection system is the secondary arrangement. So main parts are these 7 parts which we have discussed. Now let us see how to choose the transmission line voltage. Choice of voltage. Choice of voltage is very, very important. Should your bipolar HVDC transmission line be plus minus 100 kV, plus minus 200 kV, plus minus 500 kV, plus minus 800 kV, plus minus 1000 kV? How do you decide about it? The power which is flowing in a bipolar link, it is given by this equation. PDC is equal to 2 VDC into IDC. I'm multiplying it by 2 because you have a bipolar link and its voltage, say if it is plus minus 500 kV, so it is plus 500 kV minus 500 kV. So therefore, it has to be 2 VDC into IDC. Let us assume that we have to transmit a power over a DC transmission line, HVDC transmission line. The power to be transmitted is 1000 megawatts. So therefore, 1000 is equal to 2 VDC into IDC. Now we have to decide about the voltage, transmission line voltage, the link voltage. Now the link voltage will be decided by the current, the magnitude of the current, DC transmission line current, IDC, that you would like to pass through the transmission line. And this current will be decided by the standard cross section of conductors which are available in the market. In the market, you have conductors of particular standard cross sections, standard thicknesses, and according to the available standard sizes or standard cross sections of the conductors, you decide about the current. Let us assume we choose a conductor whose cross section is such that it can pass a maximum current of 1000 ampere. That is, IDC is 1 kiloampere. 1 kiloampere means 1000 ampere. So therefore, once you have chosen the current which has to be which has to flow through the transmission line, and this line has to transmit a power of 1000 megawatts. So this will very easily give you what should be the operating voltage of the link. So therefore, operating voltage of the link, VDC, is from this equation. It is PDC by 2 IDC. What is the power which you are intending to transfer? It is 1000 megawatts divided by 2 into IDC is 1 kilowatt, 1 kiloampere. So therefore, VDC, so this is 1000 into 10 raised power 6, and this is 1 into 10 raised power 3. So therefore, it is 500 into 10 raised to the power 3 volts. So therefore, the DC link voltage or the transmission link voltage is plus minus 500 kV. This is how you arrive at this standard transmission line voltage, link voltage, plus minus 500 kV. If power to be transmitted over the line is 1000 megawatt, and if the conductor you have chosen has a capacity, current carrying capacity of 1 kiloampere, the voltage at which you have to operate your bipolar transmission link is plus minus 500 kV. Okay, and once you know about the voltage of the link, so you can very easily decide about what should be the height of tower. Okay, what should be the clearance of the cross arms. So this may be your tower will look like this. This, say for example, you decide about, depending upon the transmission line voltage, it will decide about the height of tower. It will decide about the clearance of these cross arms. And on these cross arms you have the insulators. And then you pass your transmission lines through insulators like this. And then once you choose this, on both sides of these transmission lines, you have to purchase the land. You don't have to purchase only this much of land. On this side as well as on this side, there should be some clearance. So that because the line is operating at a very high voltage, 500 kV. Okay, so therefore you have to cut. This is the right of way. This is ROW, right of way, on both sides. So you have to cut all the trees on this side, over this right of way, and also on this side. This is how you decide about what should be the total land, involved with this transmission tower towards its left, towards its right. And once you know about the right of way, you purchase the land from the owner, you cut the trees around the transmission tower, and you pass the transmission line over that. Okay, that's about principal part and how to make the choice of transmission link voltage or transmission line voltage. And with this, I'm very pleased to inform you that our module number 1 is over. It gives me a lot of pleasure that in these very hard times, when our survival itself is at stake, okay, we have been able to conduct these lectures. We have been able to be connected with each other, and Alhamdulillah, we have finished our module number 1. Our module number 1 was introduction to HVDC or transmission system, historical background, and different types of HVDC, advantages of HVDC system over HVAC system, drawbacks, economic considerations, economic factors, types of HVDC links, and then principal parts or main components of HVDC systems, and finally how do we make a choice of the HVDC line voltage or link voltage. So this completes our module number 1. Now we will start with module number 2, and let me tell you that module number 2 is the lengthiest module. It's the biggest module, because in this module a lot of work has to be done. We have to understand the operation of these converters, in the rectifier operation, in the inverter operation, for various operating conditions, for 2-valve operation, for 2 and 3 valve operation, for 3 and 4 valve operation, without commutation, with commutation, and all that. And then we also have to discuss in this module, after this module, operation of converters with mal operation. I mean, whenever there is some mal operation with a converter, how to operate it, what are the various types of mal operations that occur when you deal with these HVDC power converters. Anyway, today we will start with module number 2. In module number 2, mainly we will focus on types of converters and the choice of converters that we are using in HVDC power transmission systems at converting stations. Now we have different types of converters. You have single phase converters, you have 3-phase converters. Obviously we will not use single phase converters because our transmission system, our whole utility is 3-phase in nature. So we will have to make a choice among the 3-phase converters, and among the 3-phase converters you have to make choice between 3-phase 3-pulse converters, 3-phase 6-pulse converters, and 3-phase 12-pulse converters. So therefore, the first part of this module, module number 2, which we are going to start today, module 2, you can consider it as chapter 2 also. The main part will be around understanding the operation of these converters, mainly three-phase type converters, three-phase 3-pulse, three-phase 6-pulse, and three-phase 12-pulse converters, and to choose the best converter suited for HVDC application. Okay, and try to understand the operation of these converters with the help of waveforms for rectification operation, for inversion operation, and all that. Right? So if you start with single phase converters, like as a prerequisite, you must know about single phase converters. As far as single phase converters are concerned, we have single phase half wave converters. Single phase half wave converters. Then we have single phase full wave converters. Single phase full wave converters. And in these single phase full wave converters, again, we have two types. Midpoint connection type. Midpoint connection type converter or bridge converter. Bridge converter. Now, as far as this midpoint connection type converter is concerned, here you will have a transformer with primary, and secondary will have a center tap. I hope you have already studied it in your electronics course. You have a center tap transformer, and then you have two devices. One, if it's a rectifier, we have one power diode there and one power diode here. It is something like this. This is transformer primary. This is transformer secondary. You have one device here, another device here, and then these devices are connected together and load is connected like this. Midpoint type converter. And then you have bridge converter. Now single phase half wave converter is called single pulse converter. The single pulse converter. Here P is equal to 1. Why? Because for one cycle of AC, at the output you have only one pulse of DC available to you. It's a half wave converter. And these converters, single phase full wave converters, whether it is a midpoint connection type converter or bridge converter, they are two pulse converters. They are two pulse converters. Here P is equal to 2. Because, for example, if this is your, if this is the input voltage, the output voltage will be like this. For one cycle of input AC voltage, the output will have two pulses, two pulsations. So it's a two pulse converter. We will not discuss this. You have already studied it, I'm sure, in your power electronics course. However, I would just like to, brush up your memory, your whatever your knowledge, whatever you know about these converters, and I would like you to revise these again. Because for understanding three-phase converter operation, it is very important to understand the operation of single-phase type converters. So please note down the assignment. This is your assignment number 1. Assignment number 1. Draw the power circuit diagrams and waveforms for source voltage, load voltage, source current for single phase half wave converter. and second, single phase full wave midpoint M2 connection converter. M2 converter means midpoint connection converter. And number 3, single phase full wave bridge converter. Bridge converter. Assume firing angle equal to 0. Assume alpha equal to 0 degree and alpha equal to 60 degrees. Draw the waveforms at these two delay angles. First, alpha equal to 0 degree and then alpha equal to 60 degrees. And assume a highly inductive load. And highly inductive load. Highly inductive load. Highly inductive load means that your load inductance is so high that your load current is smooth and ripple free like this. This is your load current, ID. Smooth and ripple free. It does not have any ripples. So this is the assignment number 1, and let me share one thing with you. Today we had an online meeting, first online meeting of all heads of departments and deans with director. We used one app, Google Meet application, which we downloaded on our mobiles and laptops, and we had this online meeting with our director. And it was decided in that meeting that at the end of each chapter, assignments will be given to the students. Students will solve the questions which are given to them through the assignments, and then they will submit the assignments on Google Classroom or any other platform that we are using. And these assignments will be evaluated by the course in charge, the teacher, concerned teacher, and marks will be accordingly allotted. It has also been decided that out of the 100 marks total for your subject, any subject, 30 to 35 marks will be evaluated out of these assignments only. Given the conditions, the situation outside, it's not possible for us at this stage to hold the pen and paper test. So it has been, therefore, considering all these constraints, it has been decided to hold, to evaluate the student through assignments up to a maximum of 30 to 35 marks. So if it is 35 marks, that means 35% of your weightage will be through these assignments. And I hope there will be no, you will solve these questions, you will do your assignments honestly, without any cheating, and you will submit them. I request your class representative, Mr. Junaid, to create the Google Classroom. I hope he has already created, but I am not added to that. Add all the students and myself also, send the link to us, and on that Google Classroom you are supposed to submit these assignments. Okay, so I am giving you time up to Monday, coming Monday. By Monday you must have submitted these assignments, and immediately I will inshallah evaluate these assignments and marks will be given to you. So this assignment will be out of 5 to 10 marks. I will decide about marks later on, depending upon how many assignments I give to you. So let us say this assignment is evaluated out of 10 marks. So please do it. So therefore, I will not take much time of you, and I will conclude my today's lecture here. Our module number 1 is over. Our module number 2, inshallah, we will start in the next lecture. But before starting the module number 2, you are supposed to know these things. You are supposed to know about the operation of single phase, single pulse and 2 pulse converters. That's half wave converters and full wave converters. Draw their waveforms. Whatever waveforms I have asked you to draw them. Try to understand, submit the assignments. And in our next class, we will start the study of 3-phase converters, various types of 3-phase converters. Thank you.